Okay, let's go. Good morning, everyone. Thank you for joining. This is our third session of the morning, the Focus Conference. We're happy to have you with us. My name is Kevin O'Connor. I will be co-hosting with Jake Welland. We're both from Axalta, and we're very happy this morning to have Mike Bonner with us to provide his presentation. Hi, Mike.
Hi.
I'll introduce Mike in a moment, provide a little bit of a background, but just an overview in terms of how this will progress. So we allocated roughly 30 minutes or so, 25, 30 minutes for the presentation, and we'll have 15 or 20 minutes for Q&A afterwards. As your questions pop up in your mind through Mike's presentation, feel free to load them up to the system that you're viewing right now, and Jake will feed them over to me and I will read them out at the end. So why don't we jump into this? So a quick introduction. So this is obviously, it's Mike Bonner, and he'll be talking today on leveraging the 2020 Idea of the Year to transform your painting process. And some background on Mike. So Mike is our profile speaker. Mike Bonner is the Vice President of Engineering and Technology for Clair Systems, a leading supplier of process temperature and viscosity control equipment for industrial fluid dispensing systems. A degreed electrical engineer, over the years he has spent time in a wide variety of industries, including audio systems, medical equipment, HVAC, and appliance controls, metal stamping, even the manufacture of gasoline pumps. For the last 20 plus years, however, he has focused on the science of point of use temperature and viscosity control in fluid dispensing. So Mike, we're happy to have you here. We're happy to listen to your presentation. A quick question first. You've got a great background. We love the guitars. Which one's your favorite?
I love them all. Every one of them knows different songs. And so it's great because whichever one I pick up teaches me something new every day. So I love them all. It's like asking somebody which kid they like best. But yeah, I've collected them over the years. I have a problem. I can't be allowed in the music store. And so, yeah, you're not going to get any declared favorites.
No problem. Well,
sorry about that.
Hopefully you have some time left in our 45 minutes. Maybe you can pick one of them up and
that would shock some people.
Okay. In the meantime, we'll stick to the topic at hand. So
good.
Feel free to get going, and we'll join you back in probably 25 or 30 minutes or so.
Okay, so we're on our way.
Looks good.
Welcome. Thank you for joining us. Today, we're going to introduce some exciting new technology for anyone who sprays coating onto their parts. So let's start by introducing the players. If you're not familiar with Clair Systems, we design and manufacture advanced point-of-use temperature and viscosity control systems for industrial fluid dispensing processes, and we've been doing it since 1990. During that time, we've amassed more than 3,500 active installations all over the globe. Specializing in both recirculating and dead-end systems, we handle low viscosity materials like water and solvents that are less than 1 centipoise, all the way up to high viscosity materials like sealers and adhesives that are more than 1 million centipoise. To handle these applications, we have to be able to work at pressures from 5 psi or about 0.4 bar to more than 6,000 psi or 400 bar. So who cares? And the answer is lots of folks, as you can see here. This spans myriad industries like automotive, steel, plastics, composites, nanomaterials, food packaging, pharmaceuticals, and sporting goods, just to name a few. Each successful project with demanding customers such as these has increased our understanding of the ramifications of temperature and viscosity in a host of fluid dispensing applications. Yes, this is a shameless advertisement for Clair Systems, but since many of these are critical finishing applications, it's also the reason that we're qualified to recognize cool new technology when we see it. Which is exactly what happened with SprayVision. Located in Ostrava in the Czech Republic, SprayVision was founded in 2017 on the idea of providing a means for paint applicators to literally see the outcome of their painting processes before they paint the first part, thus improving overall quality and reducing cost by reducing setup time and paint usage while increasing first pass yield by reducing rework, rejects, and scrap. This is not a simulation. It's a measurement of the actual film pattern that you're dispensing. The system was first introduced at Paint Expo 2018, held in Karlsruhe, Germany, and last November was voted the best idea of 2020 out of 171 entrants at Vodafone's Idea of the Year contest. And in spite of COVID, they've already achieved an installed base of more than 40 systems worldwide. In 2020, we signed on as SprayVision's exclusive North American distributor because we were so impressed with their innovative diagnostic technology, which is complementary to St. Clair Systems' temperature and viscosity control technology, which is designed to maintain the consistency of your process from the first part to the last. As the folks at SprayVision put it, it's not what you look at that matters. It's what you see. Now, to explain what that means, let's peek in on an introduction that we did just a couple weeks ago.
Yeah, this is SprayVision, and as we were just saying, took it over in November. This is brand new technology. This was developed in 2018 and introduced to the market in 2019. So it's really new out there. As Mark mentioned, it was developed by a team in the Czech Republic. And these are a bunch of really, really smart young guys. And they're addressing a need that's really never been touched before. So it was voted last year in Vodafone's Best New Ideas of 2020. It actually was voted #1, which is kind of cool. It's very, very unique. This is oriented for your paint customers, and it's going to address 2 key problems that your paint customers have. #1, setting up new parts and new colors. And then #2, making sure that every time they run those parts and those colors, that they get the predicted results. And this is a completely different approach to simulation and all of the things, all of the tools that are currently available. So let's jump right into it. You can see, looking at it, that it looks like a standard flatbed scanner. And in fact, if I open it up, it still looks like a flatbed scanner. This allows you to measure actual applied paint while it's still wet. It's kind of interesting. Whereas your normal flatbed scanner has a carriage that runs underneath, this does as well over a glass bed. And this is not your typical HP scanner. This is metal. This is real glass. This is good stuff. It's industrialized. It's made for an industrial environment. But this lights from above. And what you can't probably pick up well in the camera shot, this top is recessed around the outside. So there's no contact with whatever you place on the scanner. So how does this work? Well, we're all used to, in the paint industry, to shooting a test shot. You come in, you start out, and you take a test shot. Now, this is a typical gun. And this is the A3 unit, and it's named A3 after European paper sizes. There is another unit, twice as wide, that is called the A2 unit, same size as A2 European paper. It's designed for bell patterns, which are large and square, as opposed to being oblong like a gun pattern. This one's easier to move, and I don't need a wide angle lens to get it on camera, so that's why we're using this. But you would normally shoot this pattern on craft paper, and you take a look at it and you'd say, okay, I can see my pattern, it's about the right size, it's about the right density, I think I can make that work. Now, here what we've done is we've sprayed this on a Kapton foil. Now this happens to be dry, but I could have done this just now and it could be wet. I can lay it on the surface of the scanner, and then I can close the lid. And lo and behold, I don't get paint on the scanner. As I mentioned, this has a full database built into it. And it works just like the standard folder system. You can see we have a root directory here, and then we have folders underneath. We can store things in the root, very similar to what you have on your computer every day. And so this is very easy to work with. Down here in the corner, we have the camera. This actually grabs access to the capture unit. And what we're going to do very quickly here is we're going to capture this. I'll get into details on the capture in just a minute, but you could probably see on the camera that the light is on in here and it's lit from above. We are actually reading the intensity of the light coming through the paint. We talk about paint hiding a lot, but what we don't think about is the fact that even though the paint gives us good color, good hiding properties, it's still pretty translucent. The reason that it does what it does is because it's on a solid background. The light is only coming from one direction. Here, we're taking advantage of the light coming through the foil. The best part about this is the ability to scan wet. You don't have to wait for the cure process. So you can spray your foil, take your measurements, get your analysis, and be ready to make adjustments and start over again before you would ever have gotten through curing in the first place. And you're not wasting any parts. Very important. Now we can see that this went through the capture process and it actually uploaded it, it saved it, and here's our pattern. So what I'm going to do is I'm going to load that, and then I'm going to run up to spray capture. And we'll be able to look at this pattern, and you'll see instantly the difference that you can see with the foil other than what you would see on craft paper. Here we can see the original scan. The blue is all open area, but now we can see here exactly what our concentration of paint is all the way across the scan and all the way across the pattern from top to bottom. We can see it in 2D like this, and it's displayed in the common FEA heat map type thermal photography platform that we're all used to, and that makes it really easy to interpret. Where it is more red, where it's hotter, the film is thicker, and you can see that it's actually reading out in micrometers right now, microns. And that micron measurement is dry film thickness. But we can not only see it in 2D, we can see it over here in 3D. And we can grab this image, we can rotate it, we can look at it, we can see what we've got. We can see where we've got our hottest spot here, where it's the thickest. We can see what's happening out at the other ends. And we can see that our pattern is actually shifted here towards the top. So this means if I did a 50% overlap, I wouldn't get as even a coverage as I would imagine if I were just looking at this on a piece of craft paper. So that's really important to us. Now, I mentioned that we're reading out in dry film, and we're going to talk about how that happens. We're actually able to calibrate the unit, and you have to calibrate the unit for every paint and every color. And so give me just a quick second here. There. I want to get back to the camera. To calibrate, we take this special foil. It looks just like the foil that I held up before, except it has a grid on it. And we use drawdown bars that are sized to this specific grid. And you draw down and you get different film thicknesses on here. You lay this on the surface and you scan it. And then you cure it in a lab oven or whatever. Run it through your process, and you cure this. It's the only time in the process where you have to cure it. Then you lay it down on a metal substrate, and you take your standard film measurement tools that you would normally use in production, be it
alchimeter, be it Defelsco, be it whatever you're using. And you literally measure the film thickness in different areas. And then the software actually allows you, if I can find this here, we'll go to calibration. I'm going to go back to sharing the screen again. And it allows, and I'm just going to show you one here. I'm not going to go through the whole process, but this was done actually off of this. And so you measure different places, and you find the intensity in the unit, and you match the matrix. You find the square that you're looking at. Say, well, for this square, my film is read out as X, and then you enter that in here. And you can see that the blue points are actually the entered points. Having a little trouble here getting that. The blue points are actual, there you go, measured data. And then the orange is the curve fit for all of these data points. And this allows us then to convert the intensity, how much light is coming through the film, to the actual measured thickness, dry film thickness. So now the measurements were originally taken, they were scanned in the wet, measured in the dry, and then correlated here. So now I have a calibration file for this particular coating. And I just do that for all my different coatings. And I can call that up. This happens to be the one for these foils, and these were done at CFAN in Texas. They do turbine blades for jet engines for General Electric. Pretty high-tech product, very impressive facility, loads of fun. But we did this work there. And I can call this up at any time. In fact, when I scan, you can see that I've assigned the CFAN profile. And I've also assigned the CFAN calibration. Well, that means that this calibration file will be linked directly to the scan, and that's why all of the measurements come out in dry film thickness. Now, I can assign that after the scan's been done. But if I do it when I set it up, and I'm probably going to be working on a part in a color, I can set all of this stuff up ahead of time, and every scan I take is automatically assigned all the proper parameters, and it's attached right to that file. When I go to look at it later, it's going to help me. Okay, now, we looked originally at, we were looking at this. Now that's my gun pattern. It's called a static pattern. And that's important to how the gun is performing. What's really important to us is when we put that pattern in motion. So this is that same pattern placed in motion. This is called a dynamic pattern. And we're going to scan this pattern here. I should still be showing my screen so that you can see the whole process. So while this is capturing, you can take these foils and you can actually apply them to your product. You can cut them in different shapes to make them fit into curves and that kind of thing. You can attach them, for instance, on a car body or something like that. You just put the whole film on there. We did that on those fan blades, and you actually get all of what your robot path is laying down. If you have complex areas, you can see now we're processing. It will upload in a minute. Back over here. Let's say you've got specific areas, complex shapes, things that you're trying to catch. You can get the Kapton in a tape, and it is 20 millimeters and 40 millimeters, and you can just stick this right to your parts. For specific points, These are little dots that you can actually peel right off and stick right in a specific point. So if you got like the curve inside of a door, or a point on a mirror, say, right out at the point at the aerodynamic front edge, you can check that point, specific point that your customer will be checking, by simply applying points and then using the foil crop features. Now, when we put this in motion, let's go look at this pattern. This is our dynamic pattern. We've taken that original static spray shape and we placed it in motion. So let's take a look at that. And here we go. Now here we can see the pattern shooting across, and that looks pretty even. It looks pretty good. But when we look at it here, we can see that it, just like we saw before, we saw that point was off center. The peak concentration of paint was off center. That is reflected here, and we can see that that is off center. We can see it when we look at our 3D pattern. We can see that it's actually shifted, in this case, off to the right. So now we can see exactly what's happening in our laydown, okay? Now, if we take this and we transfer this to our foil, there we go. Let's say that we take this and we place this on our part, and that's exactly what we did at CFAN. We applied this right to the blade and we taped all around it, and then we went through and we did the normal robot pattern. And we look at this, and even holding this up where the light can come through it, it looks pretty good. And we're pretty happy with that. But the indications would be from this dynamic pattern and what we saw there, that it might not be as even as we think it is. And that's probably why I chose these slides to show you, right? Because they do show exactly what we're looking for. So I'm going to come in and I'm going to scan that. Now, what this means, we take the foil, we apply it to the product, we run our normal robot routines. We go in, we peel those off. We haven't cured it yet, it's still wet. The whole process so far has taken 5 minutes. We lay it down, you've seen the time it takes to capture. So we're going to add another minute or two. We're going to capture this data. And then we're going to look at it and we're going to see the result of our actual painting process on the surface of our part, because all we've done is shifted that by 20 thousandths the thickness of the foil. So now we're going to get very accurate information about the setup of our painting process. What we're actually looking at right now is, with these, we can identify the output from our specific brush settings. And then we can see that it's already captured, it's already put it back up. I'm going to run out, and I don't have to go to the database. I can just click select. I can find that one that I just did. There it is. So let's pull that up. We can see the width, we can see the height, we can see everything about the output from our atomizer for this particular brush setting. And then we can go back and we can see exactly what it looks like when it's applied to the part. And even though it looked like it should have been smooth, we can see that we have 30 microns in this area, but over here, we're actually down, there's 22, over here, 15, 14. Half of the paint that should be applied. Looked pretty good on the part, and yet, here we can see that we have a problem. In 3D, yep, there's the hole, There's the unevenness, heavy around here, big hole in our paint. Obviously, that's an issue. I mean, think about this. This is on a jet engine turbine blade. Find me one thing in the world where balance is more critical, where even film is more important. So seeing this, I can look at this. I can analyze what's happening with my robot pattern. I can go back and make corrections to my program, and then I can reapply the next foil. I can rerun that program, spray the part, pull it off, scan it, and I can see if I've successfully corrected this problem. And I still have not yet cured a part. So that multiple hour time, I mean, in an automotive plant, it can take 3-4 hours to get to the other end of the line and start taking that data, and you have to take it with an alcometer or a DePelsco or whatever. You got to take all of those different points. Here, you're not getting individual points. If you chose to measure here and it came out fine, you'd say, that's great. Maybe not even realizing, or you got out here and you said, well, I'm a little light, but it's not too bad. Whereas if I had just moved to the left or the right, just a little bit, I can see that I have real problems. This gives you the entire picture of the entire paint area. So this allows you to fine-tune your parts very, very quickly. So when you set up for a new color, you can fine-tune it and get that robot program working perfectly. And all because you were able to set up, test your brush settings, and check the way the paint is applied to the part. That leads us to, great, I got it today, it's wonderful. Next week, I want to run this part in production. So how do I make sure that I'm going to get the results that I set up today? And the answer is to make certain that your spray pattern from your atomizer matches exactly what you used for your setup. So for that, you set up a golden standard, and this provides an option for process control. I'm just going to use the metrics real quick, and I'm just going to use some files that I've got scanned in here to show what's happening. To start with, I'm going to select a project. I'll use this one. It's our training project. And then it's going to say, here is my gold standard. This is my gold pattern right here. Now, I can walk up. I can put a foil in place, and most lines, they just simply make a fixture where this always goes in the same place. You walk up and you set it down, attach it to your fixture, run your program, and the robot comes down and it shoots this pattern very quickly. It's always the same, so you always have a reference. And then you scan that. And then I run out and I bring that pattern in. And let's just say I'm going to run this one. Here's the one I just scanned. And it pops up and it shows me all of my relative measurements. And it's comparing it to this pattern. Here is the pattern here replicated, and then here is what we're actually measuring in the red. And we can see that this correlates to the volume match, how much paint was applied, the shape match, the width and height, and then the angle, whether or not this is tipped one way or the other. I should be sharing my screen so that you can see this, because what's important is that we've set limits for what our maximum deviation is. We can see here 15%. I can literally go back. I can look at this. I can hit the project manager and it will pop up, and I can set the deviation for all of these different variables And I can set the tolerance for each of these. Now, we've looked at it and said, I'm okay with 15% variation on these, and by finish will still be acceptable. But this could be at all different amounts. I could have 7% here. I could have 12% here. I could have, here I see 50% in my SB50 variable. So there's all kinds of things that I can set up in there for my specific paint projects. Here I can see that I'm out on my volume and my shape, and it's because my width is off. So now I can go back, I can make some changes. Maybe my air cap is dirty. Maybe my shaping air, and you can have one shaping air, two shaping airs, whatever. Maybe those are not quite at the right level. Maybe my flow isn't right. I can make those adjustments. And once I've made those adjustments, I can shoot another sample. I can then come back. I can run it. I can see if I've done any better. And here I can see that my pattern matches my gold standard. Now, when I reproduce that robot program, I am going to get the same results that I originally set up for. And I have wasted how many parts? 0. I spent how much time curing them? 0. So far, I've now confirmed my process and I haven't painted a part. Now, I can do this at the beginning of each shift. I can do it at the beginning of shift and at lunchtime. I can do it as often as I want because it doesn't take any appreciable amount of time to do. And so that's really important. It lends itself to other things. Let's say that I rebuild my guns every week because I want to make sure that they're in peak condition all of the time because I can't afford rejects if I'm going to make my shipments to my customer. Makes sense. But if I'm doing this, say, at the beginning of every shift and at every lunch period, so I'm getting 2 points per shift, I can store these in the database. I can create folders for that specific atomizer, even for that specific paint, but more for that specific atomizer, and I can look at the drift over time. Maybe I learned that I don't have to rebuild every week. 2 weeks is satisfactory. Now I fine-tuned my PM program so that I'm minimizing the amount of time that I spend maintaining the system while still ensuring optimal quality. It's a really important feature.
And so that's SprayVision. Again, I want to thank you for taking the time to be here today. Though we've only scratched the surface of what the SprayVision system can bring to your paint operation, I hope that we've opened a new window through which to evaluate your painting process. So I think we've got a few minutes here if there are any questions.
Hello, Michael, can you hear me?
I can. Can you
All
hear
right.
me?
I can. Great presentation.
Thank you.
Very much appreciate it. And we do have some time available here for questions, and a couple have just come in. So I hope you're ready.
Let's go.
All right. First question. How well does this method work with eStats? I believe it's eStats.
Are you referring to electrostatic painting?
I'm guessing, yes.
Okay, and I'm going to
I'm interpreting somebody's question, but I think that's a fair interpretation.
Yeah, and it's not the first time that somebody's asked that question. And in fact, the beauty of it is that it doesn't interfere with the electrostatics. Let's say I'm putting this on the door of a car. The door itself is acting as the ground and allowing it to draw the particles to the door, the paint particles. Well, all we do is we attach this over the door. It still acts much like think of it like a mule behind a plastic part if I'm doing plastics painting. And the foil I call it a foil. It's actually Kapton film. It is non-conductive electrically. So the charge passes right through it. The attraction passes right through it. But we collect the paint on the foil, which is still a solid surface, and it still allows it to do all the things it normally does. In the case of plastic parts, like I said, if you've got a conductive primer on there, the electrostatics still work right through the Kapton foil. If you've got that plastic part over a mule, again, they're very, very thin. I think I said 20 thou in there. I actually am not sure they're quite that thick, but still, it doesn't appreciably affect the impact of the electrostatics.
Okay, great, thank you. Another question here. So I think, and this is it's a bit of a broader question, but a lot of us are being pressed with the idea of efficiency and sustainability, and there's this bigger trend of Industry 4.0. And it looks like the technology you're describing ties into a lot of those. Maybe you can give a little background in terms of how this helps support initiatives towards either efficiency, sustainability, or Industry 4.0.
Well, in the first place, the ability from an Industry 4.0 point of view, the ability to fine tune your brush settings and make sure that they're always the same so that your robot simulation is now working with the actual width and overlap that you should be doing instead of the assumed fan pattern and overlap. You can actually work with the real numbers. This is going to make your initial setup more efficient. That's going to reduce your cost when you're setting up each part. And then the fact that you're able to come back and reproduce those settings time after time without painting parts, running the line, curing the parts, all of the energy and the time associated with that, the paint, the solvents, the exhaust, the RTO, all of those things are associated with those test parts, and also the scrap that's generated. If you can reduce the scrap that you're generating, then you're not putting them in a landfill, you're not having to deal with all of that. But more than that, you're not consuming that time. So now the time that you would have spent doing those setups and making sure you're right before you run job one is actually now used running job one. So now your throughput goes up. So now you're more efficient. And again, when you're more efficient, you're more effective, you've got less waste. All of this contributes to the sustainability of your process.
Got it. Great answer. Thank you. I think we have time for another question here, so I'll read it out. Does this tool work for analyzing overlapping passes, or could it be used to understand the impact of overspray?
It does. Overspray is a great subject, and this is really, I think, two different questions. We have the ability to go out and analyze the overspray area because we can see the whole area, so we can analyze the overspray. There is a feature within this tool that I didn't cover in this video just for consideration of time, and it's called droplet analysis. So we can literally go into the overspray area and we can examine the droplet pattern in there. We can examine the droplet size, the droplet volume, the number of droplets in that area. I know we hog Clair on as a way of covering up all sins, but the reality is if I'm putting clear coat over sandpaper, it's still sandpaper.
Got it.
So the whole idea is get each layer fine-tuned so you're getting the optimal results in each of your individual layers, even if you're spraying wet on wet.
Got it. Okay, thank you for the clarity. I'm sure there will be other questions after this. I think the video was very insightful. I mean, it's pretty direct, easy to understand. And I would invite the audience, if you happen to have any of the questions, to reach out to Michael Bonner directly after this for anything else. So I think that's all we have for this morning. I would like to thank you, Michael, for your presentation.
Thank you.
It was excellent. I'd like to thank the audience for joining. And just a reminder, we do have the student poster sessions and exhibition booths in between these presentations, and I invite you to join those. And the next one will be at 12:15. But that's it for today's presentation. Again, thank you, Michael, and we will be stopping the live stream.
Thanks,
Take care, everyone. Thank you.
Bye-bye now.
Bye.